Our first speaker is Fabian Haiden from the University of Miami, soon to be Oxford. He'll be telling us about Legendrian skein algebras and Hall algebras.
Okay, thanks, Ben. It's a great pleasure to be here in Edinburgh for the first time. So, it's a very highly compressed version of this talk. What is this about? Trying to combine here two things. One, skein relations. And the other higher category. And you might be looking for papers which combine these two things, might be several. Then buy your Hall algebras. There's right now only one paper that I know of who tries to do this. It's due to Cooper-Samuelson, which I stumbled across. So I'm going to talk about that, how these things should be related. And very roughly, think about this maybe as being both falling under the heading of there's some kind of quantum topology. Why they should be related is because there's only one quantum topology, there's not several flavors of that. But it's still a bit surprising. So for this audience, I want to start with kind of a bit more algebraic motivations. I want to start with Hall algebras. Because so the version of the Hall algebra that I'm going to use is this one for triangulated categories. I want to see talk a little bit about how you get there. So, of course, the most classical thing, if you have an abelian category, and assume let's do kind of the accounting version. Assume strong finiteness, the number of palms, any two object, number of extensions is finite. So finite dimensional representations over some finite field, and then you can define these. Algebra A as a basis the set of isomorphism classes, and it has structure constants for any triple of isomorphism classes. It's a number. It just counts subobjects. This is number subobjects A prime B. ABC is supposed to be suggestive of an exact sequence. A prime isomorphic to A and quotient E mod A prime isomorphic to C. This turns out to be associative. Some kind of, more conceptually, what you're doing, kind of, you're studying your category by looking at filtrations. In that category, when you form a product in the Hall algebra, it looks at all the different ways you can build an object using filtrations with these associated gradient. So this is nice, but what you really want in the subject, just play around a little bit, what you see. And I don't think this is really solved right now. That what you want is you want to define the Hall algebra of a CMOD 2 graded category. Graded, let's say, triangulated category. right? Somehow it should be bigger. So this guy should sort of sit inside here for various examples. So for instance, this famous result of Pringle, you can get half of the quantum group from representations of a quiver, the median category. Sort of get the whole thing. You expect that you need the CMOD 2 graded category, sort of stabilized 2 periodic category. And there's some kind of, that would maybe classify as more like trickery, some ingenious constructions which do this in some cases, but they're not completely general. I'm not going to solve this problem, but part of this talk will give some more hints about what's going on. Okay, but you can't get that right now. If you can't get what you want, you try to get something similar, and that is for non-periodic Z-graded triangulated categories. So this is Tolan for the finite case, and then Savage, Solomon. For the motivic. Here somehow counting the number of points of some variety, and the universal thing to do would be to take the motive of that variety. Algebra is defined over the ring of motives. But I'm going to stick with the over finite fields. In any case, so what they define is this whole algebra of a Z-graded ordinary. It's usually how you define triangle G or infinity category. With the important assumption so if this were completely general, it would solve this problem here because CMOD 2 graded is just 2 periodic version of the triangulated category. But here the key assumption is that the X groups in very low degree should vanish eventually. Finite dimensional or finite field sets, and then 0 for I sufficiently small. So it doesn't include the 2 periodic case, particular case. But so this is going to be the version of the whole algebra that will be used kind of for my result. And so how is this defined? And let's stick with finite field case. Somehow this was like an open problem I think for some years, and then Tolan figured out how to do it. It's something that in retrospect, as so often is, it's kind of very natural. It's clear how to do it. But at the time, the general techniques, there's a more general idea behind that. I'll talk about that. I think now it's very natural, but at the time it was kind of new. And so, first of all, you could write down some formula, and then I'll explain how you would get that formula, because the principles behind that will be relevant for other things in my talk. So the formula is that, and of course, it specializes to the usual one. If you have two, again, ACs will be isomorphism classes of objects, and some product. The main new ingredient is that you take into account negative X groups. Factor here, product 0 to infinity, cardinality of X minus I. H has obviously two conventions to put this one. C X minus I from C to A to the power minus 1 I plus 1. Factor which takes into account negative X groups, 0 from C to A, and then sum over all possible extensions, so alpha in X1 from C to A, and here you take the extension corresponding to the cone from C minus 1 to A by alpha. Yeah, and also there's two different versions of how you. Johan's actual formula looks a bit different. This is the version that, depending on if you think of elements of the Hall algebra either as functions on the set of objects or as measures on the set of objects. And so you get this formula if you think of them as measures. So
the vertical bars, you really mean the size of that finite set, or you mean the dimension of?
I mean actually the size of
the
so
size
it's some power of q. Yeah.
For this thing.
Yeah, some power of q.
What was the second part about below C, B?
So you think that there's some exact triangles A, C, right? And then classified by some extension alpha. And this is B. Just the object corresponding to this extension.
That's what I mean by
Shift by -1.
oh, -1. That's what it is.
Yeah, before I explain how you get this formula, maybe you know about do that. Some kind of puzzle, or some playing around with this formula. And let's take the first example that was also historically kind of for Hall algebras. If you take A, first the abelian version, if you take A to be the category of nilpotent representations, nilpotent endomorphisms. Single nilpotent endomorphism, Squibber. Then classical Hall algebra, symmetric algebra, algebra in elementary symmetric polynomials, free generator H degree. Particularly, it's commutative. In general, the Hall algebra is not going to be commutative, but in this particular case, by accident, it is. And touching this theme, which I want to talk about, this is also, you might think it's kind of some accident, but for a deeper reason, this is skein of the annulus. If you only look at sort of positive braids going in one direction, positive, the oriented. Braids in S1 2. Everything is periodic, everything is going in one fixed direction.
So, is there a relation between the Hall algebra of an abelian category and the Hall algebra of a scalar category?
Yeah, one will be contained in the other. So for the abelian category. For instance, it depends. So it just in this formula, you just in the abelian category, you don't have any negative x. So you should just reduces to dividing by size of Hom, which still looks a little bit different than this. But that difference just comes from this difference in thinking about functions or measures. And if you multiply by size of the automorphisms of the object, you exactly get an isomorphism between these two versions. Yeah, good question.
And so this statement here was about the non-cohomological one?
Yeah, now it's just for abelian first.
Do you get any other surfaces from other quivers like this? Like for instance, if you take one dot and two loops, do you get something interesting?
You put some relations, yeah. I think you can get some puncture. This much more puncture, yeah. I'll say kind of how this generalizes, but it will take a little bit more background. But first, yeah, if you look at the derived version, so Hall algebra dB of this guy, and it's still a very simple triangulated category. Let's say S is this simple object in here. Then just plugging it into this formula, you compute that s times s shifted by 1 will be s times sum, and then plus the extensions going this way, and then the identity map gives you an extension which results in a zero object. It's an object and a shift by 1 have an extension which is a zero object. Zero object is just a unit in the whole algebra. So plus q minus 1 times zero object. Right. This part comes from the trivial extension, and it's q minus 1 because it's q minus 1 multiples, non-zero multiples of the identity. But suppose the other way, you just get the trivial extension. There's no x. Particularly, yeah, unlike already for the simplest categories, it will be non-commutative. So this is a problem for us. If we want to think it's somehow related to the skein of the annulus, the skein of the annulus definitely, because you can put braids next to each other, it doesn't matter which order, you can always switch them around. So the skein, if you allow arbitrary curves, will be definitely commutative. The product on the skein is just stacking braids on top of each other. So there's kind of a little bit of a contradiction here, which
doesn't make sense. So he said again.
The skein, if you allow, like maybe not just positively oriented, but you can allow any curves or frame curves, different variants of that.
So you're multiplying you're multiplying by combining strands. Is that right? Not by the braid. I'm confused.
Yeah, this is not a tangle. It's not a braid. Sorry, this is a link in S1. This is the S1 direction. Things in here are links in S1 cross R. This is periodically identified. These two ends.
And you're multiplying them by sort of stacking them.
Yes.
By concatenating the annuli together.
Right. The general principle.
Yeah, then I understand. Yeah, thank you.
Whenever you have some surface times R, then this skein has some natural product, because you can stack things on top of each other. In general, the skein will be just a module. Okay, so I'll come back to this and say how this is resolved.
Are you saying that if you allow strands going in opposite direction, that's the problem, or is it like?
No, I mean, whatever kind of variant decorations you would want to put on here, it's always going to be commutative. Yeah, I'll come back. I'll explain. Okay, but first let me go back to this formula and explain where that comes from. So it's kind of, if you first hear about it, this maybe silly notion of homotopy cardinality, but here it's very essential. X is some homotopy type, and it needs to be very finite number of connected components, finite fundamental groups. Fundamental groups vanish in some sufficient high degree. Find some group-wide cardinality here. Let's call this X. H. Homotopy is taken into account. Sum over connected components. And take an alternating product over sizes of the fundamental groups. Multiplicative order characteristic. 1 infinity, cardinality of I x base point b to the power minus 1. Essentially where this infinite product like that. It's essentially a finite product, assuming that these guys vanish. big enough I. So relative version of that is continuous map by some finiteness assumptions. You can look at finitely supported functions on a set of connected components. Let's just send x. X is a connected component, represented by a point f of x. But there's some more sophisticated way you can go this way, which takes into account the homotopy fiber of this some f upper shriek, which f upper shriek of y. Basically, it's like a pullback, but you take into account homotopy cardinality of the fibers. X I naught with f of x equal to y to look at the points in the fiber, connected components, and then here take this homotopy cardinality, homotopy fiber f respective to this component x over y. And in practice, since you're only interested here in some alternating product, you can use long exact sequence of the vibration, and this is completely determined by homotopy groups of x and y.
So sorry, that kind of that little h out to the right. What does that mean?
It just means that this definition.
Oh, that's right. Great.
And if you just have an ordinary groupoid, then it's kind of a familiar thing that you don't count its number of isomorphism classes, but you divide by the size of automorphism group. So in the what does this have to do with PG categories? G or infinity category, infinity 1, or even higher, yeah. It's an infinity groupoid, isomorphisms, subcategory, which is a groupoid, which corresponds to homotopy hypothesis or something. Essentially, this infinity groupoid is the same thing as the homotopy type.
So may I ask, so what happens if some by I is equal to 0? So how to define? And say I is odd.
That's one element.
No, it's a group. It has at least one element.
Ah, okay. Okay, sorry.
Yeah, but like, if you had analysis, also it wouldn't help you, right? Because for infinite product to convert to go to 1, but it's just integers. If it goes to 1, then it's eventually 1 anyway. You get some homotopy type, kind of enhanced space of objects. There's some set of isomorphism classes of objects in the category. It has some refinement, which is taken into account some higher homotopy groups. Set of connected components of this will be a set of isomorphism classes. C. I 1 add some point which corresponds to an object E will be automorphisms of E. Inside X naught. Something that people higher category theory are very familiar with, is that Toan made it precise for factoriality. You can push forward, pull back. So this is not a universal way of obtaining Hall algebras. C do it in triangulated TG unity categories. Then what corresponds to now these two-step filtrations, as we had here, just looking at a subobject. In triangulated world, it just means you have a functor from the A2 category, A2 quiver, to C. The object in here is just an exact triangle in this category. And now you have functors to C and C cross C. Just sends this to either the pair CA of triangulated categories. And you can think of it, this is sort of the universal thing which gives you the whole algebra. And now, you can think of this itself as being an algebra in a category whose morphisms are spans. It's not an algebra in the sense that you can multiply things, but it's an algebra in some category. But if you want to get an ordinary algebra, then you go to this, take bases, set of isomorphism classes, and here you have C times C, so you push along this diagram. It's kind of a convolution. You get some product on linear combinations of isomorphism classes. We call these functors P, Q. This is all algebra product, which I gave you with this explicit formula over here. Conceptually, what this is computing is here the pull push. Q lower star composed of P arbitrary, which go from Hall tensor Hall, but take set of isomorphism classes, tensor product of this Q linear combinations of isomorphism classes of C. Which is this Hall algebra as a vector space. Okay, so that's where it comes, and that's kind of, now you could, instead of just sort of counting, there's many different versions of the Hall algebra, but they all come from a construction like that. And also, Hecke algebras also come from some different, it's not functors, but combination. Okay, so, and this idea will be somehow that you can push and pull these measures along functors will be somehow. I'll come back to that.
So when you phrase it this way, is there any sense that you could generalize with this quiver? You're just taking this simple to this Kronecker quiver. If you get anything sensible, if you consider just some 3-step quiver or something.
Then this functor here, right? So
Yeah.
if you have a representation of Kronecker quiver, you get many different extensions.
Yeah.
It's another fact that this category has just 3 objects. You can project to C in 3 ways.
Right.
So you get a product. And if you have, it's a good question. What happens here if I put root associativity? So there's a whole tower here, but they give you the iterated product. So okay, switching gears a bit. Legendrian knots. I'll promise this will eventually converge.
Sorry, so I have a question. So here you associate to any, let's say, K-linear Legendrian category to this, there's this system of association. Is it possible to give other system of association which also has a streak, which also have a push-pull formula?
Yeah. So what Fabian Haiden do, the ultimate thing is you look at motives over the stack of objects, and you can push and pull these things across functors, and that's how you get the motivic version of the whole algebra. And I guess that with reverse sheaves, yeah, it's a similar story, but I don't. I do not get into any cohomology or anything. I'll just stick with finite fields. So the important thing to sort of remember is this, and from this you get all versions of the Hall algebra. So a little bit about this Lagrangian knots. It's now there was this mystery about why is it non-commutative versus commutative, and this is supposed to be explained by this Legendrian condition. So you have some contact free manifold. Just doesn't. You don't really need to know what that. Locally, it's going to be. Local model is R3. Any generic one form looks like near a generic point. Then the Legendrian condition. Usually, when people study Legendrian knots, it's just inside standard R3. This Legendrian condition. Yeah, it's one form. Take the kernel of the one form, it cuts out some rank 2 distribution in the tangent bundle, and you look at curves which their tangent vector follows inside this rank 2 distribution. So curves L so that alpha vanishes. But what does it mean concretely? R3 coordinates. The most used for projection. There's different ways you can project here. This is not symmetric with rotations. And the most useful, you project to the XZ plane. It's called the front projection. So take some knot L to its front. And for generic knot, locally it will look like the function of the graph of a function from x to z. But then you have some possible singularities, which are either crossings, simple crossings, or you can have, and this should vanish. So the one coordinate which I forgot here, the y coordinate, I can just recover by looking at dz over dx. It's just the slope of the line. So in particular, if I have this sort of picture, and I have the projection, usual knot theory, you need to say which is the overstrand, which is the understrand. But in the Legendrian knot theory, there's kind of only one possible way in which they could have crossed. I mean, assuming that kind of smaller y coordinate is closer to you, then the smaller slope needs to be in the front, and the larger slope needs to be in the back. So, yeah, it's kind of the main thing in knot theory is you get some change crossings, and in Legendrian knot theory, it's only one type of crossing. It's easier. So one small extension here that which I need is grading. This G, some cyclic group. Then talk about G graded links, and yeah, it's like grading in Fukaya categories. And this is something that's really particular to Legendrian knots. It doesn't have an analog in smooth knot theory, which will kind of save this connection with Hall algebras. Just illustrate this in an example. The trefoil. We have here 4 kind of strands which go from cusp to cusp, and grading means that you are supposed to label these by elements of G. 0, 1, 2, and the rule is always at a cusp, the upper strand is 1 less than the lower strand. The rule is. Not every knot you can put this grading. Total winding number should equal to 0. Then you can put this for what should be multiple of n. And this grading is what's supposed to correspond to the shift in the triangle. Okay, so let me now. There's a version of the skein relations for the Lagrangian knot theory. Look a little bit similar, but some other ones as well. So the list them here. So that the main thing you need to say is kind of how does if you cross one strand with the other, and these have some grading here. -1. Now just simply is even. Sorry, n is even, or it's cyclic, infinite cyclic group. This, and now the strand has switched. And then if the grading is close to each other, either different 0 or 1, you get some additional terms. M is equal to n, Kronecker delta, you get a term q minus 1. This guy, and if m is equal to n minus 1, you get term 1 minus 1 over q. This looks a little bit weird. If you do the other projection to x, y, it looks exactly like the usual skein relation. Okay, so that's the other ones are very much simpler. If you have kind of a kink in your two cusps like that, left and right, following to each other, it's 0. But if this is somewhere in your link, the entire thing should be 0 in the skein. And for the unknot, q 1 over q minus 1. I mean, there's some conventions you can put here, but this is. Now you could ask, where does this come from? How do you come up with these relations? And people in Lagrangian knot theory have them, but you can also recover them. Sort of what Cooper-Samuelson did in their paper. You can recover them in a way if you know how the Hall algebra works. If you start with the assumption that Hall algebra and skein algebra are related, you can look at what kind of relations do I have in Hall algebra, and it gives you something like this.
Sorry, did you say already the Q is where does it come from?
So here Q is just some formal variable, so this should be over the ring. Z join Q plus minus 1. Q minus 1. But then I'll specialize out of prime power to compare it with the whole algebra over finite field.
But should I think in this Legendrian geometry that it's some grading and some Fukaya kind of or something? But where does it?
The Q is just a formal variable that I can be for now. And if I compare it with the category, Q will be the prime power size of the finite field.
So this formal variable, how do you derive this relation?
I'm just like trying to understand where the motivation for this relation would come from your point of view.
I mean, the structure constants for simple enough categories, structure constants will be just polynomials in Q. So if I put my size of my finite field as just some indeterminate Q. I mean, Q is, in the motivic version, Q is motive of affine line. If you do it like that. Then it's really not a number, but
Maybe I can ask you later.
yeah.
Did you say the first one is not a definition, it's computing the skein relation in the Lagrangian projection and writing it?
So here I'm taking it as a definition, but you could get it by this comparison with the whole algebra.
But okay, this is something you were.
I haven't yet explained to you how to get these relations from the whole algebra. So I'll come to that. So right now it's just kind of dropping from the sky. They were derived using whole algebra. I'll explain how you get them. Okay, so I mean, using this, you can define a skein module for a contact-free manifold by taking linear combinations of this ring of Legendrian links and then modding out by these relations. And the relations are in R3, but locally any contact manifold is R3. Get skein contact. And there's some choice here, maybe G created. So there's something which I didn't mention. Maybe I'll sweep under the rug a bit. If you want to define graded curves in a general contact-free manifold, you need some additional grading structure on the free manifold. If you just want oriented curves instead of graded curves, you don't need that. In any case, so this is a module over this ring R. And as you sort of might expect, right, that if you take the skein of R3, you just get the ground ring. Meaning that if you take any complicated Legendrian link, you can simplify it using these relations. You eventually get the empty link. It's generated R times the empty link. Which means the same thing as that there's some Legendrian not polynomial which satisfies these relations. Legendrian, it's invariant under Legendrian isotopy, not smooth isotopy, not polynomial. It's called the ruling polynomial R of L. So what's the meaning of this? You make some arbitrary relation, you get something. Yeah, it's actually counting something. What's it counting? And this was kind of there's a long history in the subject. Legendrian not theory, any papers, and then eventually it's a paper Rutherford and Seebeck and Vaslov. They associate some kind of category to this not L. I'll say what it is. Augmentation category. Some category right now, some triangulated category or infinity category. Before I define it, how is it connected to this polynomial? If you look at certain class of objects in here, rank 1 objects in this category of the link, and take overfinite field, and you take its homotopy cardinality, you get exactly this ruling polynomial. So the ruling polynomial specialize at Q is equal to the prime power. Q is your formal variable, set it equal to the prime power for this field. So the polynomial is counting objects in this some category.
So that's the C of L something 1.
Yeah, all of C of L is some triangulated category which has infinitely many objects, and then there's some rank 1 objects, which I'll explain, that there's only finitely many isomorphism classes, and then it makes sense to take this. Yeah, if you look at higher rank objects in here, what you get is some satellite invariant. Okay. So what is this category? Yeah, that's a kind of philosophy in homological mirror symmetry that every category is Fukaya category of something. Every category it's interesting. If it's triangulated category, it should be the Fukaya category or something. So this is Fukaya or Fukaya sign category. I'll give a more down-to-earth description, but this is sort of a highbrow way of viewing it. Of Lagrangian surfaces in R4, branes in R4. I take my contact R3 and add some time coordinate. And for a very small time, this surface should equal to this Lagrangian knot. So branes S the surface, so S for T very small should be this Lagrangian link L, and S for T very large should be T. So this is T. I have this Lagrangian knot, and now I have some surface whose boundary is a bit like a Seifert surface, but it's really it's a Lagrangian in the step 4, whose boundary is this knot. And there's a more elementary definition. Yeah, rigorously defining these categories takes a lot of time. But since we just have something which sort of lives in the plane basically, so we should be able to define this much simpler. And what you do, it's C of L will be global sections of a sheaf of DG categories. So more elementary maybe it's more algebraic. Yeah, taking limits DG categories is not completely easy either. A sheaf of DG categories on the real line, this coordinate x, projecting down one step further to my x-axis, and to specify the sheaf, I just need to tell you what our stocks points of R. I think this is also very reminiscent of how knot invariants are constructed. You present your knot as some composition of tangles, and you define for elementary tangles what's happening, and then you glue everything back together. So you just have near a generic point. To say what is the stock of the sheaf. Here it's the category AN, representations of AN quiver, with n vertices. The one non-generic thing that happened is I have some crossing. And here it's the category of a pair of flags in the derived sense, it's just a sequence of morphisms, which differ in one step.
So how come here seems to be the first time you made an overcrossing versus undercrossing rather than a singular crossing?
Sorry, the crossings are always supposed to be like that.
The higher slope guy was in back.
Yeah, but here I didn't put the crossing because there's always one way to resolve it.
Oh, I see.
And here also.
Okay. Sorry.
Yeah, again, there's two conventions how you protect. But there's only one way to.
Got it.
If I switch it around somewhere. So this is like in this generator of the Hecke algebra where you take a flag and you associate to it all other flags which differ from it in one step. This is like a categorical version of that. You can all look at an object in dB, on an object in dB of my ground field. It has two flags in this derived sense, so just a sequence of objects in here whose total cone is this given object, and they differ in one step. And then there's the other thing that can happen, some cusp. And here, it's a category of flags, which there's some two-step subflag, which is acyclic. So corresponding to this cusp. So some two-step subquotient is acyclic.
So here when you write dVAN now is where you insert this finite field, like dVAN.
Everything is over this finite field. Well, in this category is the finite random field. I'm not counting anything yet. But eventually it will be everything over this finite field if you want this homotopy cardinality result. And rank 1 means that just the subquotient here is a line, dimension 1, homology. C1 condition is that the subquotients of these flags are rank 1, which in this Fukaya side of the picture it means you get branes with the rank 1 local system on the entire local system.
In the middle description, you have two flags on derived category. What's inside the parentheses there?
Okay, just derived category of vector spaces. Okay, so now get to the punchline. So you have this category, which is in some ways categorifying this not polynomial in R3. And so what happens if you're not in R3? So my contribution here is that the not polynomial should be replaced by some element in the skein, some module. And yeah, I'll look at threefolds, which are sort of surface times R. So, table, the classical, polynomial invariant, and categorical. So we have this ruling polynomial so in R3. And there's this category, and this decategorification is roughly taking this homotopy cardinality, rank 1 part, it's exactly that. And this paper which I mentioned. And now if you're in, yeah, if I talk about general contact threefolds, I would need to deal with this some Fukaya category for fourfold. I'll look at the particular case where you have this algebra structure. So my threefold will be surface times R. The surface has some one form. Then you can put a contract structure on this. And then here, so you have the skein, the Lagrangian skein module. And the point is categorified by the Fukaya category of the surface. In what sense? If you take here the Hall algebra, everything is over finite field. So basically, this is the Hall algebra, but you also need to take some sub-algebra. I mean, this is something you very often do when you work with Hall algebras. It's sort of very big, has a huge basis, all isomorphism classes of objects. Usually, you pass to some sub-algebra. But then you do get this skein. Everything is C-graded. So I'm still working on too. Also, this is for Z-graded curves. I believe there's also versions for other gradings. No, here, this was some fourfold. This is just the Fukaya category of the surface, which I can also, I could talk about if I had more time. It's something fairly elementary. It's some curves, and you count disks following these curves. Different definitions, which are all not too bad. Don't need any homomorphic curve counts. And now this element of a Legendrian link in the skein has a categorification, which is there's a functor from this category of the link to the Fukaya category of the surface. And how you get this element in the skein, take kind of the counting measure on rank 1 objects in here, counting measure in the isomorphism sense. And there's some functor here, inclusion, I. And how do you get the element in the skein? You want some element in the whole algebra of this guy, you push forward the counting measure on some subcategory of the CFL. Counting measure means in the sense where you can correct some factors coming from sizes of negative x groups. Okay, so this is my table. Okay, I'll stop here. Thanks.
Are there any questions for a speaker?
So the ruling polynomial for these things in R3, is it just specialization of Hofmann polynomial?
Yeah, in the Z-mod 2 grade case, that's true. But in the other gradings, it can distinguish non-isotopic knots, which are smoothly isotopic, but not Legendrian isotopic. This famous Chekhov example, you can use the ruling polynomial to distinguish them.
So the grading, sorry, I just misspoke. The grading comes into picture how? So because you change category or what?
No, I mean, in usual, it's just you number. A grading is just you put some numbers on your knot, satisfying some rules. It's some decorated version of Legendrian knot. It's a graded Legendrian knot. And why I want the Z-graded version is because I want to compare with the Z-graded Fukaya category.
Yeah. Okay. Makes sense. It might. Well, it has some relation to what else.
Yeah, the Z-mod 2 grade case would be very interesting to figure out. But there's this problem which I discussed in the very beginning. To make sense of this whole algebra.
Did you say that there was extra structure that you have to put on a general contact free manifold?
It's
like a grading.
It's a grading. So what does it mean if you have this free manifold? It has this contact distribution, rank 2 subbundle, and you choose a non-vanishing section of that. That would be a Z grading.
Okay.
Or you can think of it as you choose a fiber-wise universal cover of the sphere bundle. And that's this rank 2. So this sort of structure doesn't need to exist, I guess, on any contact manifold. It's the same idea that what you do to get to do Fukaya categories, how to get a Z-graded category instead of just a Z-mod 2 graded category. It's the same sort of structure.
But can I ask again the question? So if I allow myself to add a lot of zigzags, so then this grading disappears, right? So then there is no
Legendrian isotopy becomes isotopy. Yes, that's why it's very important to have this relation, because if this were equal to some multiple of the straight line, all the Legendrian subtleties would sort of collapse. So you might think that this is, why is there no more complicated relation here? If I try to put something else, I'd actually just get an isotopy, smooth isotopy variant.
So basically the juice is like in this exact thing.
Yeah. So it looks like, if you look at in the XY projection, it's a small.
For the case of S cross R, do you have a front projection in general, or do you just translate this to the?
It just means any contact free manifold locally, it looks like R3, so these relations make sense. You can also easily translate these relations into the xy projection. Yeah.
Maybe a comment, maybe a trivial part of that, not the subtle part which I didn't really understand, but ask you more about that. The finite homotopy formula you wrote down is actually part of a TQFT you can define for finite homotopy types in any dimension. So given a finite homotopy type, you can choose a dimension, you can define a TQFT. Increase the dimension, you get to see more of the homotopy groups, not just their order. You can see invariant and so on. It seems that in building the whole algebra, you've used the one-dimensional case up there. You've got an algebra in vector spaces. And it seems that an obvious adjustment allows you to build an algebra object in higher TQFTs, which would see again a bit more of a structure of the category. Is there any use for that? Is there any place or categorification of the whole algebra?
Yeah, I think categorified by the whole algebra, then it will actually matter what are these homotopy groups. If you look at not motifs over your stack of objects, but you look at actual sheaves of some sort, coherent sheaves or perverse sheaves over the stack of objects, it will actually matter. The structure of this infinity stack will actually matter. But that's very scary for me. Already the motivic version is where you only care.
If there are no other questions, then there's coffee and